Okay, so let's get started. This is chapter 13, the last section, section 13.4 of aldehydes and ketones. And the last part of this chapter, namely 13.4, deals with the reactions involving aldehydes and ketones. So some of these are going to be reactions that you've already seen, and several of them will be new to you. Okay, so first let's talk about the preparation of aldehydes and ketones. It says here that the principal means of preparation of an aldehyde or a ketone is the oxidation of the corresponding alcohol. What do they mean by a corresponding alcohol? Well, if you take a primary alcohol and you oxidize it, you end up producing an aldehyde. Now, I've also told you earlier on in the class that an aldehyde can even be further oxidized to a carboxylic acid. So we'll put here carboxylic acid. Okay, and a secondary alcohol is oxidized to give you a ketone, whereas a tertiary alcohol does not oxidize at all. No oxidation will occur. And so during that oxidation process, we lose two hydrogens. Remember that in organic chemistry, oxidation is losing hydrogen or gaining oxygen. Okay, and so what we're going to see is every time we do an oxidation of a primary or a secondary alcohol, we're going to remove two hydrogens. All right, it's considered an oxidative elimination reaction because we're eliminating something from the molecule, namely the hydrogen atoms. Well, let's take a look here. It says distinguishing the types of alcohol oxidation. First of all, and this is something that we've already looked at in the class, so this should be semi-review to you, if not full review. If we take a primary alcohol and we oxidize it, we end up producing an aldehyde. And what did we lose during the process? We lost both of these hydrogen atoms. We lost this one, and then we created a double bond between the carbon and the oxygen to make a carbonyl. Okay? If you want to say, okay, well, I want to highlight this hydrogen and put the double bond like this, okay, that works as well. All right, either way, as long as you understand you're going to lose two hydrogens and produce an aldehyde. Now remember, the oxidizing agents, there's a couple of possibilities. We can use H2CrO4, which is chromic acid, or we can use KMNO4 in sodium hydroxide. And we'll just write hydroxide like that, okay? So that's potassium permanganate and hydroxide. But for this class, just writing O in these square brackets represents oxidation. So oxidation, okay? All right, there we go. Let's move on to secondary alcohol. If we take a secondary alcohol like 2-hexanol that's shown here, and we oxidize that, well, what are we going to end up with? We're going to lose two protons, and then we're going to make a double bond to the oxygen to produce a ketone. So there we go. We make a ketone from a secondary alcohol. And if we have a tertiary alcohol, it does not undergo oxidation. There's no exceptions to this. You know, there's a lot of exceptions in chemistry class, but there's no exceptions to this. You are not going to get any oxidation occurring. And the rationale as to why this doesn't occur is that when you want to affect a oxidation reaction on an alcohol, you have to have at least one hydrogen attached to the carbonyl, or the carbonyl carbon. You can see that we have two methyl groups. We don't have any hydrogens. And if you're like, well, what about the other molecules? Well, if we back up, you can see that in the secondary alcohol, we definitely have a hydrogen here. And when we go back to the primary alcohol, the carbonyl carbon has two hydrogens attached to it, okay? And so that is the criteria that is required in order for oxidation to occur. Okay, no exceptions to this rule. All right, so reactions of aldehydes and ketones, oxidation and reduction. Also, an aldehyde can be oxidized to a carboxylic acid. If we back up here and go back to our aldehyde, or was it here? We take a primary alcohol, we oxidize it to an aldehyde. That aldehyde, as I told you earlier, can be further oxidized. It can be oxidized even more to make a carboxylic acid. So we could take this and we would end up with this molecule, which is called butanoic acid. So butanoic acid, okay? So basically you end up putting an oxygen in between the carbon and the hydrogen of the aldehyde like that. All right, let's go back to that summary slide. Aldehydes oxidize to carboxylic acids. Okay, fine. Aldehydes and ketones are reduced to alcohol. So we can do the opposite, right? Not only can we oxidize primary and secondary alcohols, we can also reduce aldehydes and ketones to give us primary and secondary alcohols. We can also do addition reactions. We can add hydrogen to an aldehyde or a ketone to produce an alcohol. And then this is going to be a new reaction for you here. It says alcohols can react with aldehydes or ketones to give you hemiacetals, acetals, hemiketals, and ketals. And if you're like, I'm not even sure what those things are, well, don't worry. We're going to cover those in detail during this lecture. All right. And then lastly, it says aldehydes and ketones can react to give aldol or beta hydroxy carbonyl products. Something else we'll look at in the future. Okay, so let's get back to this oxidation of aldehydes. This is more rehashing of the same thing, but repetition is always a good thing in chemistry class. It says here that aldehydes are easily oxidized to carboxylic acids by almost any oxidizing agent. So easily oxidized that it is often difficult to just get the aldehyde to stop. Right? Usually when you take a primary alcohol, so like this, and you treat it with strong oxidizing conditions, people usually just go all the way to the carboxylic acid. It just goes past the aldehyde. But I just want to point out that there are reagents out there that can get the reaction to stop at the aldehyde. Now here in the slides, it says almost. Well, almost means not all, okay? There are some reagents, we don't cover them in this course, but just put the bug in your ear. There are some reagents out there that will affect the transformation of a primary alcohol directly to an aldehyde and just stop there. Okay, the buck stops there. All right, now remember, I told you that the possibilities for the oxidizing agent are H2CrO4, that's chromic acid, or it could be potassium permanganate in sodium hydroxide. But what I want to point out about these is that chromic acid is obviously acidic. Okay, that's obviously acidic. But if potassium permanganate is in hydroxide, well, hydroxide is a base. So there's two ways of doing this. You can do it in acid and base. Now I want you to think about this really hard. If you take an aldehyde and you oxidize it to a carboxylic acid, but the carboxylic acid is in a base, all right, what's going to happen is that when this reaction happens, this reaction that I'm highlighting with the red arrow, when that happens, you are going to produce the carboxylic acid, right? You are going to produce this carboxylic acid, okay? But then what happens is that the hydroxide is going to take off this proton and it's going to leave you with a negative charge, all right? Because if this is an acid and this is a base, you're going to end up with this ion, which will be part of a salt, and you'll also end up with water, right? Because the hydroxide is taking on this proton, so you end up with water. Now, they didn't write in a balanced equation, and oftentimes in organic chemistry, we leave out spectator ions, right? Like there's no sodium written here, but you can assume that it's there, okay? So you need to understand that when you take an aldehyde and you treat it with chromic acid, you end up with an acid. But if you take chromic acid and you treat it with if you take an aldehyde and you treat it with potassium permanganate and a base, then you end up with an ethanoate ion, or the conjugate base of an acid, okay? All right, well, with that in mind, let's keep progressing here. What about ways to distinguish aldehydes from ketones, right? They're kind of similar. They both have similar boiling points. We discussed that in the last lectures in terms of their physical properties. All right, they both have a carbonyl group. They're both polar. Okay. Well, there are ways that we can distinguish aldehydes from ketones. And the thing is that years ago, scientists were very limited in what they had as tools to help them identify functional groups in organic compounds. Now we have modern instrumentation that allows us to elucidate the structure of organic compounds oftentimes in a few minutes. But years ago, I'd say before the 60s or before the 70s, it could be very cumbersome and very tiresome to try to determine the structure of an unknown compound. And so what chemists did is they devised a variety of reactions that they could do where they could observe some kind of process with the naked eye, and they could determine, okay, well, this functional group would be present in a compound. Okay, and one of those is called the tolerance test. And if you're thinking, oh, it's old-fashioned, nobody would use this anymore, that's not true. It's still used to this day. The tolerance test is sometimes called the silver mirror test. Or sometimes we call this the silver mirror test. Okay, and what happens is that you start out with a silver ion, which is silver +1, and it gets reduced or gains electrons, right? Gains electrons reduced to a silver metal. Okay, and then that silver metal is going to make a mirror on your glassware. It makes a beautiful silver mirror. And you start out with this basic solution of this silver ammonia complex. And then again, the silver metal precipitates and coats the mirror, producing a smooth silver mirror. Now, if you're like, what the heck are you talking about mirrors, Mr. Dion? Well, the whole point is this. If you take an aldehyde, okay, and you treat it with this silver ammonia complex, which is called the Tautomers reagent, right? So this is the Tautomers test. That's what we're looking at right here. This is the Tautomers test, named after somebody named Tautomers. If you do that, if you have an aldehyde, you're going to end up with a silver mirror. If you try this same test with a ketone, for example, and it's not shown here, but if you try the same test with a ketone, you do no mirror, right? You will not see any kind of silver mirror. And so this is a proof positive. If you get that silver mirror, you can say to yourself, hey, I might not know the entire structure of the compound, but I know it's got an aldehyde in it, okay? And if you're wondering, what exactly does this silver mirror you speak of look like? Well, here is a solution, a solution of some kind of aldehyde that's in here. It doesn't tell us what the identity of the aldehyde is. But what's the whole idea is that we're trying to distinguish or determine whether there's an aldehyde here or not. And in this graduated cylinder, somebody has the Tautomers reagent, and they add it to the flask. Okay, this is called a Florence flask. We don't use these a whole lot, but they added it to the flask and they swirl it around. And look, this is the silver. Okay, silver 0. So that's silver metal. And if you're wondering, how come we don't do that in class? Well, I can tell you that it's because of the cost, right? The Tautomers reagent is not cheap because it has silver in it. It's actually pretty expensive. Anyhow, kind of an interesting test. All right, and if you're wondering, do I have to be aware of the Tautomers test? Absolutely you do. So you should know what the Tautomers test is, and you should know that when you treat an aldehyde with the Tautomers reagent, that you end up producing a silver mirror. However, if you do the same or treat a ketone with the same reagent, the Tautomers reagent, you will not get a silver mirror. Another way to distinguish an aldehyde from a ketone is to use this test called the Benedict's test, okay? So the Benedict's test, and you have to be aware of the Benedict's test. I can tell you right now that the ACS final always loves to have a question in there about the Benedict's test. And the reason why I think, and I could be wrong, but there's many people that take this class who are interested in nursing or maybe have nursing intent. And the Benedict's test used to be used by nurses, and I'll explain that more in a second. Anyhow, it says, the Benedict's reagent is simply a buffered aqueous solution of copper 2 hydroxide and sodium citrate. So sodium citrate is just the conjugate base of citric acid, okay? Now what the Benedict's reagent does, or the Benedict's test does, is that it's the same as the Tautomers reagent. It reacts with aldehydes, but not with ketones. So you get a nice positive reaction with an aldehyde, but not with a ketone. And the way that you can observe or identify that there's a reaction going on is that copper 2 hydroxide, right? This compound right here, CuOH2, this is copper 2 hydroxide. Now, this is a review of Chemistry 101, but what's the oxidation state of the copper in CuOH2, right? It's copper 2 plus. Why? Because hydroxide is -1, and there's 2 of them, so that equals a total of -2, and so you have to have copper 2 plus to balance that out, okay? So what happens is you start out with copper 2 plus, and I shouldn't have even used that color ink because copper 2 plus has a beautiful blue color, like aqua velva is what I say. It looks like copper 2 plus is blue, a nice blue color, and then when it reacts with an aldehyde, it gets reduced to copper 1 plus, and copper 1 plus is a brick red precipitate. So we'll put here brick red, like that. Anyhow, So again, the solution of copper 2 plus has a very distinctive, beautiful blue color. And what happens is the color fades during the reaction as the copper 1 precipitates and it forms a red solid. So copper 1 oxide. So again, the copper 1 found in copper 1 oxide is a red solid. Okay, there you go. So if you take an aldehyde and you treat it with a Benedict's reagent and you see a red solid being formed, you know, hey, I've got an aldehyde. If you were to take a ketone and try the same reaction, you would not see any reaction. You would just keep your blue solution of copper 2 ions. Give me a thumbs up if you follow me thus far on the old Tollens test and the Benedict's test. I can see my students here. I'll type in the chat. Hello. All right. Anybody there? All right. Thanks, Ryan. Great. Great. Who else? Greg's there. Anyone else? All right, BP. Good. All right, good group. Okay, perfect. So, you know, a couple of tests. And again, you might think, oh, that's old chemistry, but it's still used to this day. Okay. And in fact, we do the Benedict's test in the lab at PPCC. So kind of a fun one there. Now, if you're wondering about what does it look like when I do the Benedict's test? Well, again, the Benedict's reagent was used in the healthcare industry. This is a long time ago, but it was used to monitor the amount of glucose in the urine of patients with diabetes, for example. So what they would do is they would add the Benedict's reagent to the urine, and then since there is an aldehyde in glucose, right, depending on how high or low the concentration of the glucose was in the urine, it would turn, you know, dark red if there was a lot, or it would turn, you know, very light red if there was very little. And so they were actually able to qualitatively, you know, determine how much glucose was in urine, which again is something that's important because you want to monitor blood sugar levels in a diabetic patient. Anyhow, kind of interesting here. Well, let me just talk about this a little bit more. Is that you have copper 2 what? Copper 2 hydroxide, and the hydroxide ion is basic. Okay, so you're doing the reaction in base, and so when you oxidize the aldehyde, it gets oxidized to a carboxylate. Okay, carboxylate. Now, you all know what a carboxyl group is, right? A carboxyl group is the functional group of a carboxylic acid, right? This is a carboxyl. Okay, if we remove a proton and make the conjugate base, this is called a carboxylate, right? If you think about the suffix ate in chemistry, sulfate, nitrate, perchlorate, think about negative charges. All right, there we go. And again, we have our blue. We have our blue copper 2 plus ions, and then we have our red copper 1 ions. Benedict's reagent, very cool reagent. All right, let's talk about the reduction of carbonyls. And again, I told you earlier on in this class that when you just see the generic carbonyls, that means aldehydes and ketones. Whenever somebody just generically says carbonyl compounds like that, carbonyls. It says here that both aldehydes and ketones are readily reduced to alcohols. And how do we do that? We reduce them with hydrogen as the reducing agent, right? Because reduction is what? The adding hydrogen or losing oxygen. And so we're adding hydrogen here. And this is a typical hydrogenation reaction where we have to use H2 gas, okay? So hydrogen gas is H2 gas. Here is the Lewis structure of H2. It's just two hydrogens bound together, but oops, not HI. I don't know why I have acids on the brain. Anyhow, it's just two hydrogen atoms bound by a single covalent bond, and that reaction requires a catalyst. Palladium or platinum or nickel, any one will work. And I went over this reaction with you earlier on in the class, and the way that you can think about this is if I redraw my generic structure of my ketone or aldehydes in here just so I can edit it, what's happening is the first thing is that you end up removing one of the double bonds like that. Okay, so you remove the double bond, I should say, not one of the double bonds. And then from your hydrogen, from your H2, okay, you're going to add one hydrogen on the oxygen and the other hydrogen on the carbon like that. And what I have in this red box is identical this alcohol shown right here. It's the exact same thing, okay? It's just that my hydrogen's down here, theirs is up there, but it's the exact same thing, okay? Reduction of an aldehyde or a ketone. First, we erase that pi bond, and then we add a hydrogen to the oxygen and a hydrogen to the carbon of the carbonyl group. And there, my friend, you will end up drawing the correct product. Okay, so a little bit more about addition reactions. It says the principal reaction is the addition reaction across the polar carbonyl bond, just like the hydrogenation that we looked at. But now we're going to talk about adding an alcohol, okay, to a ketone or aldehyde. And in order to do that, we need a catalytic amount of acid. And the way that we represent a catalytic amount of acid is we put H plus and we put it in these square brackets right here. That's when you see that, you know that you mean you have a catalytic amount of acid. Now it says here the product of the reaction is a hemiacetal. I'll show you what that is. But a hemiacetal is quite reactive. And then it can undergo a substitution reaction with another hydroxyl group, okay? And then we can end up producing an acetal since the reaction is reversible. But before we can even proceed with this at all, you need to learn what a hemiacetal and an acetal is. Let's take a gander here. This identifies both of them at the bottom. Okay, so I want you to pay close attention because I've taught this class enough to know that sometimes students struggle a little bit with acetals and hemiacetals. So let me show you the easiest way to remember these. Is that if you have a hemiacetal, okay, you have a carbon and it looks like you have an alcohol on it and an ether on the same carbon, okay? It's not an alcohol and an ether, right? I always teach you that in organic chemistry, you have to take the big picture view, and the whole thing is called the hemiacetal. But if that helps you, and I have found that that helps students, you just say, okay, here's a carbon, it's got an alcohol on it, and it has an ether on it, like that. That means a hemiacetal. So you could even put here alcohol and an ether on the same carbon, like this. Okay, so that's hemiacetal. And acetal is when you do the same thing, you have a carbon, but instead of an alcohol in the ether, you've got two ethers on the same carbon. Okay, so it's like you have an ether, and another ether on the same carbon, like that. Okay, so now that you've seen the structure of the hemiacetal and the acetal, let us take a look at the addition reaction and see how it works. And you'll be able to, or be expected to be able to identify the products, you know, and I would highly recommend practicing drawing the products of an addition reaction of an alcohol to an aldehyde or a ketone to first produce a hemiacetal and then an acetal. Okay, so let's take a break. Deep breath. Done. Okay, break's over, and let's take a look at this reaction that's going on in this green shaded rectangle here. So first we're starting with an aldehyde or a ketone. The first step, the first thing that happens is an addition reaction across that aldehyde or a ketone, but now you're adding an alcohol across it. Let me show you my, kind of Mr. Dion's shorthand method of figuring this out. Look, I start by drawing the aldehyde like this, okay? I don't like to include my carbon, but there you go. Okay, so I start by drawing my aldehyde, and I'm going to add this molecule, right? I'm going to add the hydrogen and the OR group. Okay, so how do we do that? Well, the first thing I'm going to do is I'm going to erase one of the pi bonds, okay, like that. On the oxygen, I'm going to add the hydrogen like this, and on the carbon, I'm going to add the OR group like that. If you look carefully at what I have here, it's the exact same molecule that's shown there. Okay, that's a hemiacetal. Take a look carefully again, and you'll notice that this carbon, okay, that I haven't drawn in, and I can even put the letter C there if it helps you, it's got an alcohol on it and an ether. Okay, so what took place there is you took an aldehyde or a ketone, you reacted it with an alcohol, a catalytic amount of acid, and you produce a hemiacetal. That's the first part of the reaction, okay? That's the first part. Give me a thumbs up if you follow me just on that much, okay? No more than that, just the first part. Anybody with me on that? Cha-cha-cha-cha-cha. All right, good. Okay, so this reaction, this whole addition process is kind of broken up into two steps. Okay, the first step is after you've made the hemiacetal. So once you've got the hemiacetal, you take that hemiacetal and it reacts with a second molecule of the alcohol. Okay, here's an alcohol, here's an alcohol. This is just a second molecule of it. And we can put here again an alcohol. Okay, now it's a little bit different. Okay, a little bit different for the second step. Let me run over it with you. You're going to start, or I'm going to start, I should say, by drawing out the hemiacetal the exact same way that they have it OR. What do they have? OR3. Doesn't matter. Anyhow, what you have to remember, you guys, is that in the second step, what's very different is that you end up producing this little molecule here that we call water. Okay, and I know you all know what water is, but where does the water come from? The water comes from the hydroxyl in your hemiacetal, and it also comes from the proton of the alcohol. So then what's left over is that you have this OR group and you attach it to this carbon here. Okay, now if you look carefully at the product, the acetal, what have you got? You've lost, there's no hydroxyl group on it, but the OR4 group is attached directly to it. Okay, so that's what happens. So first step is the aldehyde or a ketone plus an alcohol, catalytic amount of acid, you make a hemiacetal. That hemiacetal reacts with a second molecule of the alcohol. You have to use a catalytic amount of acid again. And now you produce a hemiacetal, but you also produce water. There's no water produced in the first step, only in the second step. Okay, give me a thumbs up if you're like, you know what, Mr. Dion, lock me in a room for, a couple hours maybe. Give me some time to practice, and I'll have it, Man, I don't expect anybody to nail this reaction in 5 minutes. No, I'm not insane, okay? I expect that my students are going to have to study. We'll have to look over it a few times, okay? It takes everybody a few passes to get the old hemiacetal and acetal formation, okay? Don't ever sit there and think, well, I'm the only person that thinks that this is kind of complicated. It's organic chemistry. Of course it's complicated, all right? So never feel like you're alone. You're definitely not, okay? Even I think organic chemistry is complicated sometimes. Let's see here. This slide is nothing more than some examples just to show my students. That's all it is, and they come directly from the book. Just a little bit of practice. So let's look at some practical examples here. It says the product of the addition reaction is a hemiacetal followed by an acetal. So let's look at what's happening. This is like the first step, okay? Where's my pen? This is, oh, good. I'm losing it. There we go. This is the first step, okay? There we go. The first step, we're taking an aldehyde. It's just propanol, so aldehyde, okay? We're treating it with methanol, which is an alcohol, okay? I have my catalytic amount of acid. I'll put acid catalyst like that. What happens? I ended up removing or breaking the pi bond, okay, one of those bonds in the double bond. The hydrogen went onto the oxygen, and the CH3O went onto the carbon. Don't believe me? Look at the hemiacetal. I promise you that's exactly what happened, okay? All right, so we ended up forming a hemiacetal. We did not form any water. Give me a thumbs up if you follow me just on the first step. Just the first step, not on the second step yet. Like New Kids on the Block, step by step, right? Okay, good. Okay, just first step. Now let's take a gander at the second step where we form that beautiful acetal. Okay, we start with our hemiacetal. We add another molecule of the alcohol, right? We use our acid catalyst. Acid catalyst. We're going to have to form what? Water as a product in the second step. Where does that water come from? It comes from the hydroxyl group. Maybe I should circle it in blue to be color coordinate. Comes from here, and then the other hydrogen comes from here, okay? So then what's left over? That tells you that this CH3O is going to attach itself to the carbon. Don't believe me? Take a look at the acetal, right? All that is different is now you have two OCH3 groups, okay? Before we move on, let's examine the hemiacetal again. Look, here's the carbon. It looks like it's got an alcohol on it, and it looks like it's got an ether in the same compound. Let's look at the acetal. Here's the carbon with the oxygens attached. It looks like I have an ether here, and it looks like I have an ether there. Okay? I think that is probably the easiest way I can distill the whole concept of hemiacetal and acetal formation. And you might be wondering, why is this so important? Like, what do I have to know about hemiacetals and acetals? Well, one of the reasons is because later on in this class, we'll do an entire chapter devoted to carbohydrate chemistry, just carbohydrates. And we'll see several hemiacetals and a few acetals show up in that chapter. Okay, here's some more examples, okay? You never have too many examples in organic chemistry. Here's an addition reaction with a ketone. So what are we starting out with? We're starting out with a ketone, propanone, and an alcohol. Okay, we have our acid catalyst. What are we going to do? We're going to break one of these pi bonds. We're going to add a hydrogen to the oxygen, and we're going to add this CH3CH2O to the carbon. Don't believe me? Here it is in the hemiacetal. Okay, so back to my hemiacetal. Let's examine that hemiacetal closer. It looks like I've got an alcohol and an ether on the same carbon. Looks good to me. Okay, then you take the hemiacetal, you react it with a second molecule of the alcohol. Okay, you've got to form water as a product. Where does that water come from? It comes from the hydroxyl on the hemiacetal, and it comes from this proton. And so then you must form a bond between this oxygen and the carbon. Don't believe me? Look right here, okay? Here's that new bond. So I have an ether here, and I have an ether here like that. All right. Again, this is the simplest possible way that I can, anyway, as your instructor, the simplest possible bits that I can distill it into. All right. Okay. Well, with that in mind, let's take a look at a special kind of hemiacetal formation that's called an intramolecular hemiacetal formation. Everything that we looked at up until now, if I back up a slide, these are intermolecular hemiacetal formations, right? Because this reaction, the hemiacetal formation, occurred between 2 molecules, right? Just like international, it's a relationship between more than one country. Well, if I have an intranational relationship, that means it's inside the same country. And so if I have an intramolecular hemiacetal formation, that means that the hemiacetal is being formed inside the same molecule. How would that even happen? Well, in order for that to happen, you have to have a molecule that has an alcohol and an aldehyde or a ketone in the same darn molecule. Okay? The same exact strategy applies. When we want to draw the hemiacetal, what are we going to do? We're going to remove one of the pi bonds. We're going to attach the hydrogen to this oxygen. Here it is right here. And then this oxygen is going to attach itself to the carbon like that. And in this case, we end up forming a ring. We get a cyclic hemiacetal. And as I told you, that in the carbohydrates chapter, we're going to look at hemiacetals, and they will all be cyclic hemiacetals. And so this same kind of thing can happen in a molecule like glucose, for example. Okay? We get intramolecular hemiacetal formation. Here's a picture of what goes on. It says here that this reaction is important in the chemistry of carbohydrates, where hemiacetals are readily formed. So if we take our molecule, D-glucose, if you've taken biology, and I'm sure that somebody who's hearing my voice has studied biology, you might have recognized glucose. You might have seen glucose in this kind of structure. This is called a Haworth projection. This is called a Haworth projection, where it shows glucose as a 6-membered ring. And then this one here, this one over here on the far left, this is called a Fisher projection. Okay? And what happens is D-glucose drawn in the Fisher projection is what's called the open chain form, right? It's not a cyclic structure. But what happens is when you have that open chain form in solution, you end up forming a bond between this oxygen and this carbon, and this hydrogen ends up going on the oxygen like that to form your hemiacetal. If you're wondering what the heck is going on right here, all they're doing is taking this molecule and they're bending it or twisting it in such a way that you can see how this hydroxyl is actually quite close to the carbon of the carbonyl in order for that reaction to occur. So what happens is the lone pair of the oxygen actually forms a bond to the carbon, and you end up breaking this carbon-oxygen bond. And then finally, this hydrogen ends up going on the oxygen like that to produce a hemiacetal. Again, don't believe me that it's a hemiacetal. Let me prove it to you. If you look at the carbons labeled carbon 1 in alpha D-glucose and beta D-glucose, and if you're wondering what's the significance of alpha and beta and D, we'll talk about that in the carbohydrates chapter, but you don't have to stress about that for the next exam, okay? If we look at that carbon, look what's attached to it. It's got carbon, oxygen, carbon, right? That's an ether, carbon, oxygen, carbon, right? An ether, and it also has carbon, oxygen, hydrogen. It has an alcohol. Okay, so that proves that these are what? These are hemiacetals. All right. Here's some examples of the formation of a disaccharide from two monosaccharides. And this disaccharide is one that you've probably heard of. It's beta lactose. And I think that something like 2% of people who are, or 20% of people maybe, I don't know. No, how does it go? Is it 20% of people? No. It's a small percentage of people under the age of 2. Virtually nobody is lactose intolerant. But by the time you get to people who are 80 years old, so I think that it's something like at 80 years old, 20% of the population becomes lactose intolerant. So if you make it, to that far in life, a lot of people can't enjoy things like ice cream because they're lactose intolerant. Anyhow, what the heck was I talking about? If you take a molecule of beta D-galactose and beta D-glucose, what happens is you have a hemiacetal, right? I'm going to circle that right here. This is a hemiacetal, and this is an alcohol. And what did we say when a hemiacetal and an alcohol react? Well, before we looked at it, the reaction, we said, okay, when you treat a hemiacetal with an alcohol, you've got to have a catalytic amount of acid. Well, I can tell you that in the human body, you're not going to find catalytic amounts of, strong acids like sulfuric acid. So this is actually an enzymatic process, right? This is formed by an enzyme. And if you're like, I'm not sure what an enzyme is, I've heard the word before, but I'm not entirely sure what that means. I'll just tell you that an enzyme is a biological catalyst, and it's basically a type of protein. And we will look at the structures of enzymes in more detail later on when we do a whole chapter on proteins, okay? So you take those two sugars, you take the hemiacetal from the galactose, it reacts with one of this, specifically this one highlighted in pink, this hydroxyl or this alcohol from the glucose, and you form what's called a glycosidic bond. Now, a glycosidic bond is a type of hemiacetal. A glycosidic bond is a hemiacetal. It's just a special class of hemiacetal because it's a hemiacetal that's formed between two sugars. And if you're like, how do you know it's a hemiacetal? Well, again, let's look at carbon number 1 here. You see that you have carbon, oxygen, carbon, right? Like an ether there. And then you also have carbon, oxygen, carbon here. So it's like you have 2 ethers on that particular carbon. And so beta lactose is a hemiacetal, and we call the bond with that hemiacetal in it, we call that the old glycosidic bond, okay? And if you're interested in carbohydrates, again, I promise you that later on in this class, in chapter 21, in chapter 16, we'll do a whole section about carbohydrates. And if you really want to get ahead, you could watch my videos that are posted to my YouTube channel that cover that chapter in its entirety. We're getting close to the end here, but before we wrap up section 13.4, I need you to know what a keto-enol tautomer is. And tautomers is probably a new word to most of you, are isomers. So it's a special type of isomer which only differs in the placement of a hydrogen atom and a double bond. So just a hydrogen atom and a double bond. We change those two things and we get what are called keto-enol tautomers. Now the keto form as you could probably guess, has a carbonyl in it, right? Because keto, ketone, right? Ketones have a carbonyl, okay? Whereas the enol form has the double bond. And you're probably thinking, okay, well, enol, alkene, alkenes have a double bond. Yeah, and you'd be absolutely right, okay, to think that, okay? If we look at the enol, so this is an enol form, where does that word come from? You have an alkene, so you have the ene, and then you have an alcohol, right? So the enol. All right, well, let's get back to this enol business forming from a ketone, okay? So if you have a ketone, we call this the keto form right here. If you change the position of what? Of the double bond and this hydrogen, right? It tells you right here. You change the position or the placement of a hydrogen atom, the one I have circled in yellow, and a double bond. So if we move the double bond in between the two carbons, and if we move the hydrogen over onto the oxygen, we get the enol form, okay? And you should probably be aware of the fact that the keto form is usually the most stable. What does usually mean? There are exceptions. We don't go over those exceptions in Chemistry 102. This is just a reaction schematic that's found at the end of the chapter. It covers the reactions that you have to know from chapter 13, okay? So let's kind of take a quick peek at it. It says here that you have to know about the preparation of ketones. Ketones are prepared from the oxidation of secondary alcohols, whereas aldehydes are prepared from the oxidation of primary alcohols. We use an oxidizing agent, which we can denote as oxygen in these square brackets, okay, to do that. Then it says oxidation, okay? It says that you can oxidize an aldehyde. And what do you get when you oxidize an aldehyde? You make a carboxylic acid. Whereas a ketone, this is not readily oxidized, okay? We can't just take a ketone and simply treat it with, chromic acid and oxidize it any further. It won't happen, okay? How do we distinguish between an aldehyde and a ketone? Well, we could use either one of these tests, the Tollens test, which is the silver mirror test, or the Benedict's test, which is where we take copper 2, which is blue, which is found in copper 2 hydroxide. And then as the aldehyde gets oxidized, the copper 2 gets reduced to copper 1, found in copper 1 oxide, which is red. All right. What else? The reduction of aldehydes and ketones is just the reverse of the oxidation, right? An aldehyde can be reduced using hydrogenation. Right? This is a hydrogenation reaction. Hydrogenation doesn't matter if you're reducing an aldehyde or a ketone. An aldehyde will give you a primary alcohol. A ketone will give you a secondary alcohol. And then lastly, what we looked at tonight was these two sections here. First, the addition reaction, the addition of an alcohol to an aldehyde or a ketone to form a hemiacetal, and then an acetal. And I should even put here plus water when you make an acetal. And then finally, aldehydes and ketones can exist as keto and enol forms. We didn't look at any reactions to do with keto or enol forms. You just have to be able to identify what's a keto form and what's an enol form. This is just another summary of the aldehyde and ketone reactions. You have to know about the oxidation of an aldehyde to a carboxylic acid, the reduction of aldehydes and ketones using hydrogenation conditions, so that's hydrogen, gas, and palladium, platinum, or nickel as a catalyst. Addition reactions, the formation of a hemiacetal and acetal, which we went over in quite a bit of detail. The cyclic hemiacetal and acetal, which I told you was this is an intramolecular reaction, whereas this one is an intermolecular reaction. And then finally, the keto-enol tautomerization that we looked at just a few minutes ago. A picture is worth 1,000 words. And here are some of the reactions being shown in equations. An aldehyde being oxidized to a carboxylic acid. An aldehyde or a ketone being reduced with hydrogen. Here they've chosen platinum. And if the person had put palladium or nickel, that would be perfectly acceptable. The addition reaction, which I spent quite a bit of time on this evening, taking an aldehyde or a ketone, reacting with an alcohol to produce a hemiacetal, and then reacting it with the second molecule of an alcohol to produce an acetal plus H2O. And then finally, the tautomerization, which is just the change in placement of a hydrogen atom in a double bond, going from a keto form to an enol form. Here are some practice problems that I recommend taking a look at in our textbook. I've chosen mostly problems that have the answers to them in the textbook. And that's it. That covers section 13.4.